So in today's sessions, we're mainly going to be focusing on OSPF, the Open Shortest Path First protocol. And one of the key differences between what we saw yesterday with EHRP and OSPF is that OSPF is an open standards-based protocol, as the name implies. It's an open shortest path first protocol, which basically means two things. It's an open standard. It's defined by RFC 2328, which is OSPF version 2. If you wanted to see the real detail behind the protocol, like you need to see the packet format or how actually the flooding procedure works or any of the real nitty-gritty details, this is going to be one of the best resources to look at. There's also a book that is written by the guy who actually wrote the protocol, whose name is John Moy.
Oh, really? It was in Dijkstra?
No, it uses the Dijkstra algorithm. And we'll talk about the difference between the two of them, because the algorithm itself is not related to IP networking. The algorithm is a mathematical search, and then this guy used that algorithm that was already there and just applied it to this application. So this book here is written by the guy who actually wrote the protocol. So this is one of the best resources out there if you want to get more detailed information about it later. The other one that's really good is the Routing TCP/IP Volume 1. This guy here, Jeff Doyle, has a lot of really easy to understand explanations about these protocols. So once you go through the exam type prep stuff, and if you still want to learn more about this, then I would definitely recommend this one. And then also Routing TCP/IP Volume 2 covers BGP, multicast, and then some other topics. But otherwise, for the very detailed stuff, we're not going to get too much into the actual packet level format. But if you wanted to see this, you can get that from the RFC. It's OSPF version 2. The other reason that it is called OSPF, so it's open, it's an open standard, and it uses the shortest path first algorithm, which is the Dijkstra SPF search. We'll see the main difference between EHRP, which we saw as a distance vector protocol, and OSPF, which is a link state protocol, is that in EHRP, when the routers are sending updates to each other, they're advertising networks. They're advertising prefixes and their lengths and the different attributes. In the case of OSPF, we're trying to build an overall map of the network. And we represent these as the states of the links between the routers in the network. So basically, we're trying to figure out what are all the different interconnections between the routers. And then based on that, we can take this data and put it into the SPF search and then result in what we call the shortest path tree, or the SPT. Other feature, just like EHRP, it is a classless protocol, which means that it supports both variably length subnet masking and summarization. But there is a strict hierarchy that goes along with OSPF. So when we look at some of the summarization features, it's much more limited as to where you can actually do this as compared to EHRP or to RIP. Because there's certain requirements of what the database structure is, so that when everyone runs this SPF search, they end up in the same result. If for some reason two routers have a different view of the network, when they run SPF, they can end up in different results, and then you would have a traffic loop. This is the reason that sometimes OSPF is described as being able to cause transient loops, where a transient loop is a temporary loop in the network that occurs while the devices are trying to agree on what the new topology looks like. In the case of EHRP, it's not possible to cause these, just based on the way that the updates are exchanged and the way that the calculation works. But we'll see the key main difference between the two of them is that at any given time, OSPF routers are going to have an overall view of the states of the links in the network, or basically an overall map of the topology. Now, just like EHRP, the ultimate goal of using this is that we want to build a loop-free topology so that we don't have to use manual static routing or manual policy routing or use some non-scalable protocol like RIP or RIP version 2. So the shortest path first algorithm, this is what it's going to solve for us, that it's going to calculate what is the loop-free topology to figure out how we get from point A to point B in the network. Other reason why you would want to use it is that it's standards-based. that with EIGRP, it's a Cisco proprietary implementation, which means all of your routers and switches have to be Cisco in order to run EIGRP. But OSPF is going to be supported by all of the vendors because it's standards-based. The other key point is that it's very highly scalable. And the way that it accomplishes this is through a hierarchy that we call the areas of OSPF. This is one way that we can hide some of the details of the topology so that the routers don't have to have detailed information about every single link in order to calculate their trees. So when we look at the difference between a single area in OSPF and multiple areas in OSPF, what we're trying to do is make the network more scalable, be able to add more routers, be able to add more links, but still be able to guarantee that the network is going to be loop-free. We also see that OSPF can have fast convergence. It's not going to be as fast as EIGRP in those cases that EIGRP has the backup paths calculated, those feasible successors. But along with some other certain techniques we'll talk about, like bidirectional forwarding detection or layer 1 sonnet protection, there are cases where you can get OSPF to converge in less than 1 second. But generally, it takes more design in order to get this to work than it does with EIGRP. So EIGRP is kind of plug and play with the convergence. OSPF is going to take a little bit more thought to get it to actually do that. One of the reasons it does this is because, like EIGRP, it actively tracks the neighbors that are on the links through the neighbor adjacency process. So before you send updates to me or before I send updates to you, we have to agree on this relationship that we're going to exchange routes, and then we're actively going to be tracking each other that if you don't receive my hello packets, eventually you're going to say I'm no longer on the network, and then you're going to have to start to reconverge. We'd also see that OSPF has event-driven updates, which basically means that if there's a change in the network, you're going to tell the other routers about it. Where in the case of RIP, normally when there's a change, you have to wait until a very long period of time, like 3 minutes or more, before the network can actually adapt. Where with OSPF, or in the case of EIGRP as well, if there's a change in the network, I'm going to tell the devices specifically what that change was. I don't necessarily have to exchange all of the routes or all of the link states. It's just going to be the ones that are related to those new changes. Another key feature of this is that the update is efficient as compared to some of the legacy protocols like RIP or IGRP, where just like EIGRP, it does use a reliable transport, and it does use both multicasts and unicasts for its updating. This means that devices that aren't running OSPF, like your end hosts or maybe other switches, they don't have to listen for the OSPF updates. So when we actually look at the packet format, OSPF is going to be using IP protocol number 89, and the updates go to the addresses 224.0.0.5 and 224.0.0.6. So just like EIGRP, it has its own layer 4 protocol, or its own layer 4 transport. So as I mentioned, the other feature that it has is a bandwidth-based cost metric. So when we compare this to RIP's metric of a flat hop count, or IGRP's legacy metric, generally this is better because it's going to give you more visibility of the network. It's not as granular as EIGRP's is, because EIGRP looks at the lowest bandwidth of the link, or the bottleneck, plus other attributes like the delay. But essentially we're going to take a bandwidth-based cost, whereas the bandwidth is going up, the cost is going down, and then we simply add that value together on a hop-by-hop basis. Another key feature is that it supports security in the control plane, which means that before we establish an adjacency, we could ask the neighbors to authenticate, either with a clear text password or an MD5 encrypted password, an MD5 hashed password, so that we can stop unauthorized routers from adding routes to the network or deleting routes from the network. So as I mentioned, just like with the EIGRP, this really is going to be a requirement of the routing protocols. There's never a case where you would want to run dynamic routing without doing authentication. Another key difference between EIGRP and OSPF, and this is one of the reasons a lot of times that OSPF is chosen over EIGRP, is that it is extensible. What this means is that for other applications that the network wants to use in the future, someone can write an extension for OSPF because it's standards-based, where EIGRP you can't do that because it's proprietary code. And one of the big things that OSPF has been extended to use is support of MPLS traffic engineering, which is a way for generally in service provider networks to use their bandwidth more efficiently and to get fast convergence if one of the devices in the network goes down, because we can basically choose manual paths of how we route from point A to point B. You cannot do this through EIGRP. MPLS traffic engineering, you cannot.
So, sorry, why does OSPF have to care about MPLS just going one layer down?
Because MPLS runs on top of IP, which means that you need IP routing to work first before MPLS can exchange its label numbers. So the way that MPLS works, it creates what's known as a forwarding equivalency class, or FEC. A FEC is a label number, where the label number is just a decimal number, like the label number could be 20. And then this is associated with an IPv4 prefix, like 1.2.3.0/24. MPLS has provisions to assign these label numbers, like 20, 21, 22, etc., but it doesn't have a provision to advertise routes, because they figured you already have your IGPs to do this, like OSPF or IS to IS. So they're in charge of advertising the topology information. Then MPLS does these label bindings. Then when you actually move the traffic, you can use these numbers to switch the traffic between the interfaces.
So how does OSPF, like you said, there's an extension.
Specifically, it's through what's known as the opaque LSAs. Their LSAs number, I want to say that they're 8, 9, and 10. That it's basically special encoding of extra information you need on the link, because what MPLS traffic engineering can do is allow you to make basically any arbitrary decision you want of how the traffic gets from point A to point B. And in today's networks, a lot of enterprises are starting to run this because it gives you a lot of control of how traffic moves through your network. But let's say we have a basic topology that router 1 is trying to get to router 2. And we have, let's say that these are all 100 megabit per second links in the network. So from the routing protocol point of view, there's going to be a limited number of options that we can send the traffic here, where maybe router 1 is going to say, for flows between router 1 and router 2, I always choose to go this way. Or maybe it's because these other interfaces, let's say the one in the middle is a gig link. When the routing protocol makes this decision, it's going to choose whatever is the shortest path from the source to the destination. So the problem you might run into is that these links could be, let's say, 100% utilization, and then these ones are near 0, because the routing protocol can't account for these ones. The only way you could get it to do that would be to make this link look like it was 100 megabits per second, but then you end up in an equal distribution of 1 to 1 to 1. And that's not really what you want, because your gig link is higher, these ones are slower, so you can't really solve the problem, where either one link is really highly utilized or all of the links are underutilized, so it's hard to fix this design. But what MPLS traffic engineering allows you to do is say that I'm going to build a tunnel that goes between two endpoints, between router 1 and router 2, and I might have requirements on this where the tunnel is going to request 50 megabits per second of bandwidth. And I need an additional tunnel that goes between maybe someone who's behind router 1, let's say router 6 and router 7. And the tunnel between the two of them wants to get, let's say, 150 megabits per second. When the tunnel tries to route out this link, the routers would say, well, there's only 50 left. And if it tries to route out this link, they would say there's only 100 left. So this tunnel could automatically choose to go this way based on its bandwidth requirements. So it allows you to do a lot of flexible things that you could say, do reservations of the network, that when you're moving traffic between two endpoints, I want to guarantee that you're going to get this amount of bandwidth. And then you route it based on how much is actually available on the links.
So these attributes are,
These attributes are encoded inside the opaque LSAs, and that's the key.
so you would see those LSAs being sent.
You would
but
see
that-
those
they
LSAs
have
being
nothing
sent.
to do with your IDPs.
They have nothing to do with your IGP, right? Yeah, but they're still being sent. What this is called is the constrained shortest path first calculation, where it means that you're adding additional attributes like the bandwidth requirements of the tunnel. Or sometimes what this also can be used to denote is what's considered a shared risk link group. And what this is basically a layer 1 function of the network, where let's say that we have long haul links that are going from Los Angeles to Chicago and LA to Dallas, and then we're going from there to New York, or maybe we have some, I don't know, we're going from LA directly to Detroit and then to New York. Where when you look at the service provider's network from a layer 1 point of view, sometimes what you'll find is that multiple physical circuits actually follow the same physical fibers when you're going over a long haul, because what they do is basically take these signals and they try to multiplex them together into one physical link. It's what's known as either coarse wavelength division multiplexing or dense wavelength division multiplexing. Basically, the idea behind this is you're trying to shove as much bandwidth into a single physical link as you can. But the problem is that if the link from LA to Chicago and the link from LA to Dallas physically go over the same fiber, if this link goes down, it also means that this link goes down because they're part of the same actual physical cable. So what you can tell the network is that when you make routing decisions, you could group these two together in that shared risk link group, where basically the risk is saying that if one of them goes down, it automatically means the other one goes down. So the network makes decisions based on layer 1 information as well, not just based on layer 2 information. But the idea behind this is that if someone wants to add these additional attributes, they can do it with OSPF. You can't do it with EHRP because Cisco is the one who controls the code. Now, if we compare this to the distance vector routing of RIP version 1 or RIP version 2 and the legacy IGRP protocol, these ones use what's known as the Bellman-Ford based algorithm. Basically, this means that I tell you all of my routes, you're going to tell someone else all of your routes, and so on and so forth, but you're only going to know what the connected neighbors are telling you. So in RIP or IGRP, you don't have an overall picture of the network. You only know what the directly connected neighbors are telling you. Sometimes this is called routing by rumor, where whatever information I learn from you, I just have to assume that that's correct. I don't really know the details about what's going on from me to get there. Typically, the entire routing table is also going to be periodically advertised. Like in the case of RIP, it's going to be sending the whole table every 30 seconds, which is going to be a big scalability issue. That if you had 10,000 routes in your network and you were using RIP, it means it has to broadcast 10,000 routes every 30 seconds, which is going to be a big waste of processing. It's going to be a big waste of bandwidth as well. Another big problem is that the loop prevention is very simplistic in the distance vector protocols, where it uses basic split horizon logic or poison reverse that says when I learn a route from you, I'm not going to advertise it back to you. Or when I learn a route from you, I'm going to advertise it back with an infinite metric, which would be poison reverse. The problem is in certain failure circumstances, when you actually use these and then go to reconverge, it takes a really long time in order to get the old information to age out of the network. So convergence in RIP may be somewhere in the order of 5 minutes for a network failure. Where in the case of OSPF and EHRP, we can get them to converge in less than 1 second. So this is where our link state protocols come in, where technically EHRP is a variation of a distance vector protocol, but it's considered advanced distance vector. because it has some of the attributes of distance vector and of link state. The actual link state ones are the two variations of OSPF and IS to IS, or the intermediate system to intermediate system protocol. This one, OSPF, was developed specifically for IP version 4 routing. IS to IS was developed about the same time for the Open Systems Interconnect protocols, which are known as the connectionless network services, and the connectionless network protocol, CLNP and CMNP. Basically, these are the equivalents of TCP and UDP. So it was a different protocol stack that was basically designed to do the same thing. Eventually, this one lost out, so these protocols aren't used anymore. CLNS, CLNP, CMNP, these ones aren't used. But IS to IS was then extended, which with what is known as integrated IS to IS, which is IP version 4 extensions. So both IS to IS and OSPF behave very similar because they're both used for IPv4 routing, and they both use the Dijkstra shortest path first algorithm. The main difference between them is that IS to IS is typically used for service provider routing, because if they were originally running these OSI protocols, they were already running this stack. So they converted to this as opposed to redesigning from scratch with OSPF. Most of the time in enterprise networks you don't see IS to IS because generally there's a lot more just information in general available about OSPF as compared to IS, and a lot of the engineers are just more familiar with OSPF. But effectively they do the same thing. So they run the shortest path first algorithm, which is going to give them a guaranteed loop-free path in the network. Both of them are also going to advertise the states of the interfaces or the states of the links, technically not the routes. Where the overall idea about these two protocols is that we first need to build a map of the network. This is what OSPF considers the OSPF database. So the database is a map of the network. We take the map, or we take the database, put it into the shortest path first algorithm. The result is the shortest path tree, which we then actually use to route the traffic. But this is the big difference between EHRP and OSPF, that at any given time, the routers have to agree on what this picture of the topology looks like. So from me to get from point A to point B, I know about every single interface that I have to go through in the network to get there. Since everyone is going to have the same picture of the topology, and since they're all running the same calculation, the SPF, they're all going to end up in the same result, which is the same shortest path tree. So in order for this to work, similar to EHRP, the first step of link state routing is to form neighbor adjacencies. This is to figure out who are the routers that are running the protocol, and then we're going to advertise different attributes of the links. In OSPF, we call these link state advertisements. In IS to IS, we call them link state packets. Basically, it's the same thing. I'm telling you what are the different attributes of my connected interfaces, and also what other routers am I connected to. The ultimate goal of this is to form an overall picture of the network, or what we consider the link state database. The link state database is basically a graph of the network, or a map of the network, that we can then use to run the SPF algorithm and ultimately come out with the same shortest path tree. So the key is that this protocol only works if everyone has the same copy of the link state database. So when we look at the verification of OSPF, at any given point in the topology, if I say show IP OSPF database, it should be exactly equal to any of the routers who are participating in the same link state area. Question?
In one area, we have 6 routers. R1, R2, R3, R6, right? Does R1 know R6, which link the R6 is connected to?
So if you have just connected a line like this, so let's say we're trying to get traffic from A to be. What router 1 knows is that I'm a router in the area, and I have this interface, I have this interface. On this interface, I have an adjacency with router 2. Router 2 has 2 interfaces, and it has an adjacency with 1 and 3. 3 has 2 interfaces, it has adjacencies with 2 and 4, likewise on and on and on. So router 1 knows when it builds the map of the network, it basically knows this entire topology, it knows this entire map.
So that's, yeah.
So it takes this as the input to SPF, and then the result is going to be the tree, which actually tells you how you route the traffic. But the key is that to do the calculation, everyone needs to agree on this picture. This is what makes up the link state database. That everyone knows that router 1 and router 2 have a link connecting each other. Everyone knows that 2 and 3 have a link connecting each other. Where in the case of EHRP, the only thing that router 1 would know is that B is reachable in that direction. But it doesn't know how 2 is actually getting to B. OSPF is going to know this end to end, though. Specifically, the first step to get this to work then in OSPF is going to be to figure out who are the neighbors. So we need to figure out who are the routers that want to run OSPF with us, and we need to exchange the topology information with them to tell them what are the different states of the links. Once we do that, we can choose the best path, and we do this by running the shortest path first algorithm. Then we go through basic neighbor and topology maintenance, just like in EHRP. That if there is a change in the network later, OSPF needs to learn about this. So the first portion is where we figure out who are the neighbors and how do we tell them about the different links. Just like EHRP, we're going to use a hello protocol to figure out who are the neighbors on the links. Where the transport uses IP protocol number 89, so it has its own protocol instead of TCP or instead of UDP, and it sends them to either 224.0.0.5, 224.0.0.6, or a unicast destination. We'll talk about this in more detail later. When is it going to use which one? But ultimately, the routers figure out that they're on the same segment and they're going to run OSPF. Once the routers figure out that each other are there, they're both OSPF routers, they need to agree on a bunch of different parameters in order to form the neighbor adjacency. Only once the adjacency is negotiated, then we can exchange the link states and build the database. So next we would then need to know what are these different attributes that we need to negotiate in order for the adjacency to work. Some of them need to be common attributes, some of them need to be unique values. We'll see that in certain circumstances as well, not all of the neighbors are actually going to form adjacencies. So just like EHRP, they're technically 2 different states where you can have a neighbor and you can have an adjacency. All adjacencies imply that they are neighbors, but not all neighbors are necessarily adjacent. This is where the vast majority of problems are going to come in with your actual implementation of OSPF. That if there's something wrong with one of these attributes, the routers can't form the adjacency and then they can't exchange any of the updates. Some of the unique attributes would include the router's identifier and the interface's address, where if 2 routers have the same ID, they're not going to be able to form an adjacency, because this is what ultimately identifies them in the map of the database. Then the interface address is pretty self-explanatory. If I have the same IP address as you, we're not going to be able to send packets to each other because we can't address each other. Some of the common attributes, this is where the list starts to get a little bit more complicated. First of which, we need to agree on an area identifier. This is ultimately going to control who is in the same flooding domain of OSPF, which means that if there's a change in the network, devices in the same area are always going to have to know about that change. When we look at inter-area OSPF, the idea is that devices in Area 1 don't need to know all of the details about devices in Area 2, so we can hide some of that information and it's going to make the network converge a little bit faster or converge a little bit more efficiently. So we need the area identifier. We also need the timers, which are controlled by the hello interval and the dead interval. Hello interval would be how often do I send you these packets saying I'm here on the network. The dead interval is how long I'm going to wait before I say that you are no longer there. In OSPF, these two values, they must agree. So two routers that are forming an adjacency, they always have to agree on both the hello interval and the dead interval. In the case of EIGRP, those are independent values. We then have the interface's network address. This basically means the subnet. So the two routers have to be on the same subnet to form the adjacency. We would also have to match the MTU. This is going to prevent some cases where I can send you packets that are large or too large to the fact that you can't actually receive them. So if one router's MTU is 1500, which is typical for interfaces like Ethernet, but for some reason on the other side, they're using a large MTU, like a jumbo frame size of 15, let's say like 1512, that when this side sends the packet to the 1500, it's going to have to be dropped as it comes in the interface, because Ethernet won't be able to accept it. OSPF tries to detect this, because if I can't send you packets, then how am I going to send you the details of the topology? So it basically sends you a log message saying, we can't establish the adjacency because there's an MTU problem. You need to fix this anyways, because otherwise you're not going to be able to properly communicate. Okay, the other one is the OSPF network type. We'll talk about this in a little bit more detail later. The authentication would be, are you using a clear text password or are you using an encrypted password? What's known as the stub flags, which we'll see later is used for filtering in OSPF, and then some of the other optional capabilities. Like in the case of Cisco's implementation, they can advertise something that is known as non-stop forwarding or non-stop routing. This would be used if you had two different physical route processors in your chassis, like dual supervisor cards in a 6500. That if one of those goes down, the OSPF process on the other one is supposed to take over. But the two neighbors would tell each other that they support this. So that if you lose the adjacency, the convergence is going to be different if you're trying to switch over to a redundant supervisor. So in order to actually establish the adjacency, we're going to be sending these hello packets. The hello packets are sent out every hello interval, where different interfaces are going to have different defaults for this. Like an interface running PPP is going to have different timers than an interface running Ethernet. Where inside the hello packet, the routers are going to be telling each other what their identifier is, what their area ID is, what is the interface address, and what is the subnet mask, so what's the local network, what is the interface's priority. This is going to be used for an election process that is known as the designated router and the backup designated router. What are the timers of the hello and the dead intervals? What's the authentication? What's the designated router or backup designated router's addresses? What's their IP? Then other additional options like the stub flags, which would be for filtering. And then the router IDs of other neighbors on the segment. This last one is going to be important when we actually establish the adjacency. This is what allows the routers to go into the two-way state, or basically acknowledge that they received each other's packets. So when I send a hello to you and you send a hello back to me, you acknowledge that you got my hello by putting my identifier in your own hello. This is one of the ways that OSPF makes its transport reliable. So to actually go through the states of forming the adjacency, OSPF defines 8 different states as part of the state machine. That basically is the logic that the router goes through to find the neighbors, to exchange the routes, and then finally say that we've synchronized the topologies, and now we can run the shortest path first calculation. First one we start at is the down state. This basically means that you haven't received any hellos from the neighbor, the same as if OSPF is disabled on the interface. Then we go to the attempt state. This is going to be used when we're using unicast hello packets, which is mainly going to be for non-broadcast multi-access medias like frame relay. We'll talk about that in more detail later, though. The other one is going to be the init state, which says that I've received a hello packet from the neighbor, but I don't know that they actually got my packet. This is the one where they first realize that there's another neighbor on the segment, that we're going to try to now initialize the OSPF process. This is when I would hear a hello from you, but I don't know that you've gotten my hellos yet. The way we figure that out is by going to what's known as the two-way state. The two-way state essentially says that if router 1 and router 2 if router 1 and router 2 are trying to establish adjacency, router 1 sends out a hello. At this point, this puts router 2 into init, saying that I know there's another neighbor that's running OSPF. We're now going to start the process. Router 2 replies with its own hello, and it says inside of this that I heard about router 1. This is what puts router 1 into the two-way state. Basically means that it knows that router 1 or router 2 got its hello. So it's essentially the acknowledgement. By putting router 1's identifier inside of its own hello packet, they know that the communication is bidirectional. And this is what the two-way state says. We'll see that in some cases, this is where the adjacency state machine stops. That if you form a neighbor relationship but not an adjacency, the routers would be in two-way state and they don't go any further. But routers are actually going to form a full adjacency. They now go to the X start state, where they're trying to figure out how are we going to exchange the database or the actual link states of the routes. Basically, this is to determine who's going to start what the sequence number is. That's just going to be able to make us keep track of what's the current copy of the database. It doesn't really matter who becomes the master or who becomes the slave, just that one of them is in charge of keeping track of the updates back and forth between them. Then we go to the exchange state. This is where we're actually sending the information about the database. And this uses what is known as the database descriptor packets, or the DBDs. A database descriptor is then going to basically tell the routers what are the different links that I know about. Then during the loading process, this is where the routers actually send the link states. It's kind of a minor distinction here, but the idea is that you can end up in a circumstance where when a new router comes into the network, it doesn't need to receive the full database from all of its neighbors. And this is why there's a difference between the exchange and loading. So let's say, for example, that the network looks like this, where we have links between router 1, 2, 3, and 4. So the neighbors form the adjacency. They build the map end-to-end of the topology. So right now, all 4 of these routers agree on what the link state database looks like. If a new connection comes up, let's say between router 1 and router 4, there's no reason that we need to exchange again this link state, and this one. Because the routers already agreed on what this map of the network looks like. The only one that needs to be added is the new one. This is why there's a difference between the database descriptor that tells you what are the link states in the database and the link state request and link state acknowledgement, where you actually tell them this is the details behind it. Because in a design like this, it's more efficient when the neighbors add this new link to tell the other ones, I have a new link. This is what it is. So router 1 is going to tell this to 2, 2 is going to tell this to 3, 3 is going to tell this to 4. But likewise, this is going to happen in the other direction. 4 tells 3 that there's a new link, 3 tells 2 there's a new link, 2 tells 1. The idea is that we're trying to exchange the information about this new interface that came up. If it turns out that it takes less time for router 3 to learn the link state advertisement this direction, it's going to ignore the one that came from router 2. Likewise, if router 2 learns the link state in this direction first, it can ignore the one that came from router 3. So they will always send each other the database descriptor saying, I know about this link, but you only need to request the information about it from one of the neighbors in the topology. Because at the end of the day, everyone agrees on the same map. Whether I got the information about the map from this guy or from this guy, it doesn't matter because the information is going to be identical. And this is one of the key distinctions between OSPF and EHRP. In EHRP, you're only going to be learning what the directly connected neighbor is telling you. But in the case of OSPF, what we're basically advertising is router 1 saying to router 2 that I have a link that goes from R1 to R4 with these attributes, like this IP address, this mask, this cost. This is the same identical information that router 4 is sending. It says there's a link between router 1 and 4 that has an IP address and a mask. It has a cost value and it has other attributes. When these advertisements get sent around the network, they're the same no matter which direction they're coming from, because everyone agrees on what the state of the link is.
So which one gets discarded?
It depends on which one comes in first. So OSPF doesn't use split horizon. It uses a really complex flooding procedure that it goes through basically all these if then else statements that says if this happens, then go to the next line and continue on and on through the search until it figures out, do I accept this link state or do I discard it? The details of it are kind of out of our scope, but if you want to see specifically how they do the advertisements, this is defined in the RFC as the OSPF flooding procedure, which is the flooding procedure. The idea behind this is that since we're not using split horizon, there's a big logic that the router has to go through to figure out, should I accept this advertisement or not? So first it figures out which is the newest copy. Do I need to install it in the database? What do I do next once I actually received it? What happens if I receive my own advertisement back? Because since there's not split horizon, it's very possible that I send an advertisement out that direction and it somehow loops back around to me. And there's basically every possible case they have accounted for here. And eventually it's going to work itself out. Question?
Yeah, so what's the difference between LSPD and DDD?
The link state database is they're both related to the database, but the specific term is the link state database. This is basically the entire map. So this is the map of the network.
Or the topology?
The map of the topology, right. The link state database is the input to SPF. So it's the data set that you put through the algorithm. The output from SPF is the SPT, the shortest path tree, where the idea behind this is that the overall map of the network might look like this. Router 1 to 2 to 3 to 4. So this is the map of the network. But now we have to figure out how are we actually going to send the traffic. The shortest path tree is then going to be a subset of this. where the tree might look like this, where we go from 1 to 4 to 3 to 2. But the key is that at the end of the day, all of the routers agree on what the tree is, because they all had the same input to SPF, which is the link state database. The database descriptor is just one of the ways that you can exchange the actual portions of the database. So I send you a descriptor, I say, I know about router 1. If you already know about router 1, you're not going to ask me for information about that. But if I say to you, I know about router 1, and you don't already have that, you send me a request saying, give me the details about router 1, and then I send you a link state update saying, these are the details about that router that I know.
The DVT subset of the LSD.
Right, yeah. So if we were to visualize this establishment between the neighbors, first thing that's going to happen is that the process starts in the down state, because no one has sent hellos, no one has received hellos. Router 1 sends a hello out. This is going to cause router 2 to go into a knit state. Router 2 says, I heard a hello from router 1. Inside of it, router 1 told me different attributes, like this is my area identifier, this is my router identifier, this is my IP address, this is my IP subnet, this is my subnet mask, all these other attributes of the hello. Router 2 replies to this. It says, I'm router 2, this is my attributes, this is my area, this is my identifier, etc. This is what causes router 1 to go into two-way, because router 2 is acknowledging that I received the hello to begin with by putting 1's router ID in the hello. Router 1 says we now need to exchange the database. This is where they determine a sequence number. At this point, it doesn't really matter who wins the process. One of them is going to say, I'm the master. One of them says, I'm the slave. They're the one that just keeps track of this sequence number to make sure that the database gets synchronized properly. This is part of the reliable transport of OSPF, that when I send you an update, you need to send me an acknowledgement, and we'll keep track of this along the way so that at the end we can guarantee that the information is the same. Now router 1 is going to say, this is the contents of my link state database. This is the database descriptors that's happening during the exchange. This would be router 1 saying, I know about router 3, router 4, and router 5. But I don't tell you what I know about them. I'm just saying I know about these routers. If router 2 already has an adjacency with 3, 4, and 5, it's not going to need that information. It would be redundant. This is where we have the distinction between the exchange and the loading phase. The loading phase is where you say, for some reason I didn't have that LSA in my database, so I need you to send me the details. This is where I send the link state request, and the response is the link state update. So it's me asking you, can you send me this detailed information, and then you actually giving me the details.
How did it know there is an LSA that didn't match?
Because they tell each other first what are all the contents of the databases. This is during the exchange phase. So router 1 says, I know about these link state advertisements. If router 2 doesn't already have those, it needs to ask for them. So it makes the updating procedure more efficient than just sending all of the routes, because you already might have some of the portions of the database and you don't need to receive it again. Finally, once this process is done, then they go to the full state. They're saying the databases are synchronized. We can now go to our actual calculation, because at this point we've agreed that we have the same input. Okay, any other questions up to this point?
So you could actually see two routers skipping the exchange state?
They could skip, they would go through all of these states, but depending on how much information they already have, that's going to control how many updates are actually sent and how many are received.
Okay.
So they're still going to go through all of the 8 states. It just might take you much less time to go through them if you already have some of the information.
But at any point in time, you should only see either init, full, because the exchange and, what was that?
When you look at the...
Loading, they are transient.
They're all transient, right. When you look at the show IP, OSPF, neighbors, there's only 2 states that you should see. You should see either two-way or full. Anything other than this, it means they're currently converging or there's something wrong. So if the network is already converged, either they're going to be in the full state, meaning they have the adjacency completely done, or they're in the two-way state because they don't need to form an adjacency. Okay, this one we'll come back to and talk about more later, in detail more later. But basically what this is for is when you have the designated router. So let's say that you have 4 routers on a LAN segment. Router 1, router 2, router 3, and router 4. So this is router 4 up here. Router 4 is the designated router. This means everyone establishes an adjacency with them. If these routers are not the DR and they're not the backup of it, which is the backup designated router, these neighbors don't form an adjacency. They'll be in the two-way state because they know about each other, but they don't need to exchange the database. They only exchange the database with the designated router. And we'll look into more detail exactly why you would want to do that in OSPF.